Okay, this lesson is going to be about Taylor series generated by f at x equals a. So really what happens here is if you want to make a Taylor series for a function at a, everything is the same as taking a MacLaurin series. You take the nth derivative, evaluate it at a now instead of 0, divide by n factorial, and then instead of multiplying by x to the n, you multiply by x minus a to the n. So in something like this, if I wanted to create a Taylor series for e to the x at x equals 2, I want to first say, well, f of x is going to be e to the x, which means f prime is e to the x, and therefore so are all the other derivatives. And if I evaluate any of those at x equals 2, I'm going to get e squared. So if I want a Taylor series for e to the x at x equals 2, I'm going to do the 0th derivative over 0 factorial x to the 0. Done. Plus the first derivative over 1 factorial x to the 1. But instead of x to the 1 now, it's going to be x minus 2 to the 1, because I'm not centered at 0, I'm centered at 2. Then e squared over 2 factorial x minus 2 squared. And then e cubed over 3 factorial x minus 2 cubed. And then if I want the general term, it's just going to be oops, I meant e squared, not e cubed, pardon me. Then if I want my general term here, it's just going to be e squared over n factorial x minus 2 to the n. And that's it. So everything stays the same as what we did in the other video on MacLaurin, except instead of x to a power, you get x minus 2 to a power, or x minus 4, whatever you happen to be centered at. Okay? So now if we move down here to example 2, instead of giving you a function, I just tell you about the function. So let f be a function that has derivatives of all orders for all real numbers. Assume that f of 3 is 1, f prime of 3 is 4. Oh, so this time what they're giving us is they're giving us the function value, its derivative, second derivative, and third derivative. These will become my numerators. So A, write the third order Taylor polynomial for f at x equals 3 and use it to approximate f of 3.2. Okay, I can do that. So if I want the third order Taylor polynomial, I'm going to put it down here. My third order Taylor polynomial, I'm going to call it t of x just to give it a name. And t of x is going to be the 0th derivative over 0 factorial x to the 0. Done. Plus the first derivative, 4, over 1 factorial x minus 3 to the first. The second derivative over 2 factorial x minus 3 squared. The third derivative over 3 factorial x minus 3 to the third. That would be the third order. Order and degree are going to be the same for these. Okay. So there's my Taylor. I'm going to simplify it because I have to plug something into it, so I might as well simplify. So this is going to be 1 plus 4 times x minus 3 plus 3 times x minus 3 squared plus 2 times x minus 3 cubed. They want us to approximate f of 3.2. So f of 3.2 is approximately t of 3.2. And t of 3.2 is going to be 1 plus 4 times, now I'm running out of room here, so follow along. If x is 3.2 and I plug it in here, 3.2 take away 3 is 0.2. Plus 3 times 0.2 squared plus 2 times 0.2 cubed. And we're going to plug that all into a calculator here, which, where is mine? I think it's on my desktop. There we go. I should really pull this down here while I'm thinking about it. You guys can watch me pin this to my task bar. Yeah, okay. All right, so here's my Smart View calculator here. I have this cool thing that lets me show full screen, so that's neat. So I have 1 plus 4. 1 plus 4 times 0.2 plus 3 times 0.2 squared plus 2 times 0.2 cubed. I think that's right. Let's see. Yep. And so now I hit enter and 1.936. 1.936. Ta-da! All right, there's my third order Taylor polynomial, and I approximated 3.2. Now write the second order Taylor polynomial for f prime at x equals 3 and use it to approximate f prime of 2.7. Well, what we did in some previous lessons is we said the nice thing about polynomials is their derivatives are so easy to take. So if I have t of x here, I can just use t prime of x to estimate f prime of x, because if t is an approximation for f, then t prime is an approximation for f prime. So t prime of x, I'm going to take this guy's derivative, is going to be, let's see, 4, and then plus this is going to be, bring down the 2, so it's 6 times x minus 3 to the first. And then I'm going to bring down the 3, 6 times x minus 3 squared. So there's the second order, because it's 2 and x squared, Taylor polynomial for f prime at x equals 3, and use it to approximate f prime of 2.7. So f prime of 2.7 is approximately t prime of 2.7, which is equal to 4 plus 6, I can write a 6, there we go, plus 6 times negative 0.3, 2.7 minus 3 will be negative, plus 6 times negative 0.3 squared. I didn't mean to hit that one. There we go. 4 plus, hello, why are we not typing? I don't know. Well, that's weird. Let's try this again. Sorry, you got to watch my, see, there it is now. Silly calculator. So 4 plus 6 times negative 0.3 plus 6 times negative 0.3 squared. Perfect. 2.74. Wonderful. Does the linearization of f. Now, quick thing, the linearization of f means the tangent line for f, and that is actually something we already have. It's right here. The first two terms of a Taylor series are the linearization of f. So does the linearization of f underestimate or overestimate the values of f near x equals 3? Well, a linearization is like a tangent line. Is a tangent line an underestimate or an overestimate? Wait, this sounds familiar. So if I have a curve and I have its tangent line, this tangent line is below this curve because this curve is concave up. So how am I going to tell if f is concave up or concave down? I need its second derivative. I need its second. Oh, wait a minute. They gave me the second derivative. It's right there. The second derivative of f at 3 is 6, which is positive. So therefore, f is concave up, right? So therefore, f is concave up. So the linearization is an underestimate because f is concave up. So for part C, I don't know why I'm going backwards, but for part C, we'll write it up here. We'll say it's an underestimate because f double prime of 3 is greater than 0. And here's a great diagram to illustrate that. So here's something that kind of brings everything together. Here's the new stuff. Here's the stuff we talked about before when we did series and then we took their derivatives. And here's some old stuff, tangent lines versus concavity. All right, how am I doing on time here? I'm doing pretty good. Turn the page. Whoop. All right, so for this next page here, I have that. Let's make it a bigger screen here. Here is a polynomial, okay? It's at order 4 for a function at 4. Assume f has derivatives of all orders for all real numbers. Okay, so it means I can take as many derivatives as I want. Find f of 4 and f triple prime of 4. Okay, now pay attention. So if I want f of 4, f of 4 is part of this polynomial. So I'm going to pull some things out. This 7 right here is technically f0 of 4 over 0 factorial, right? Because the coefficient, the first coefficient, is the 0th derivative over 0 factorial x minus 4 to the 0. Well, 0th derivative doesn't mean anything. Doesn't that just mean f of 4 is 7? Yeah, it does. F of 4 is 7. Okay, so I got that part. Now they want f triple prime of 4. Well, I would take the third derivative as part of this third term, right? And this third term is supposed to be the third derivative of f at 4 over 3 factorial x minus 4 to the third. This term has that form, which means f triple prime of 4 over 3 factorial equals negative 2, because the coefficient of x minus 4 to the third should be this. And the coefficient of x minus 4 to the third is negative 2. Therefore, this fraction equals negative 2, so the third derivative is going to be negative 2 times 3. No, I'm sorry, it's times 6 really, but negative 2 times 3 factorial, ha ha ha. Negative 2 times 3 factorial is negative 12. I cracked myself up. There's your third derivative. In other words, the derivatives are hidden inside the coefficients of each of the terms, okay? If you wanted, say, the fourth derivative at 4, you would say, okay, my fourth derivative at 4 is part of this 6. So 6 equals the fourth derivative at 4 over 4 factorial. So I just do 6 times 4 factorial, and that would give me the fourth derivative if I wanted it. Okay. All right. B, write the second order Taylor polynomial for f prime at x equals 4 and use it to approximate f prime of 4.3. Well, if I want the second order Taylor polynomial, that really just means I want the derivative of p. So I'm just going to take p prime and take the derivative. So that's going to be negative 3 plus 10 times x minus 4 to the first, bring down the 2. Then minus 6 times x minus 4 squared. And they want the second order, so I stop there. There's the second order Taylor polynomial at x equals 4. And I'm supposed to use it to approximate f prime of 4.3. So f prime of 4.3 is approximately p prime of 4.3, which is equal to negative 3 plus 10 times 0.3 minus 6 times 0.3 squared. And let me get my calculator so I don't make a mistake. All right, so I want to view this. I don't want to see that. There we go. Make it smaller so we can see it. So if what am I doing? Negative 3 plus 10 times 0.3, which is really 3, minus 6 times 0.3 squared, which is 0.09. Negative 0.54. Ta-da! Okay. Write the fourth order Taylor polynomial for g of x, which is the integral from 4 to x of f of t dt at 4. Okay. Well, what that means is I am going to basically take the antiderivative of this, and how do I want to say this? When I take the antiderivative, I'm just going to do the whole add 1 to the power divide by the new power thing, and I don't need to worry about a plus c, because what's going to happen is I'm going to take the antiderivative and then plug in x and 4. And when I plug in x, I would have written them initially as t's, so when I plug in x, they just all become x's. And when I plug in 4, all these become 0. So let me try and write it out here. That'd probably make more sense than me saying it. So I have that. Let me make the screen bigger so I can see everything. So let me use a new color so nobody's confused. You're probably confused already. Just bear with me. Okay, so I am going to integrate from 4 to x f of t dt. In other words, p of t dt. So I'm going to do 7 minus 3 times t minus 4 plus 5 times t minus 4 squared minus 2 times t minus 4 to the third. Now they want me to write the fourth order, which means once I take the antiderivative, I want it to say x to the fourth. So I'm going to stop here, because when I take the antiderivative of a cubic, I'm going to get a quartic. So I'm supposed to take the antiderivative of that, plug in x and 4. So if I take the antiderivative with respect to t, I get 7t minus, this is going to be, let's see, 3 times t minus 4 squared, add 1 to the power, divide by the new power. Then 5 times t minus 4 cubed over 3, and then minus 2 times t minus 4 to the fourth over 4. So there's the antiderivative. I'm going to plug in 4 and x and see what happens. Well, when I plug in x, I really get 7x minus 3x minus 4 squared over 2 plus 5x minus 4 cubed over 3 minus, I'm running out of room. Oh no. Hang on, let me fix it. Oh, no, that's not going to help. Ah! There we go. Here we go. Sorry, I'm fixing it. Okay, and then minus 5, and then minus 2x minus 4 to the fourth over 4. That's when I plug in x. Then I need to subtract what I get when I plug in 4. Well, when I plug in 4, I'm going to get 28, 0, 0, and 0, right? So this really becomes 7x minus 4 minus 3x minus 4 squared over 2 minus 5x minus 4 cubed over 3 minus 2x minus 4 to the fourth over 4. Whoa, whoa, Mrs. Bibber, this said x. Where did you get x minus 4? From here. This is 7x minus 28. Isn't this 7x minus 28? Yes, it is. You're right, it is. When you go and you take the antiderivative to save yourself time, you don't need to do this. You could jump right to here, right to what's in the purple, because basically all we're doing is we are taking this function up here. Let me erase it so you can actually see what's up here. We are taking this function up here and then just doing the add 1 to the power divide by the new power. But this right here, you just have to think of as 7x minus 4 to the 0. And then when you add 1 to the power and divide by the new power, you get the 7x minus 4, so it's consistent. So if that kind of blew your head wide open, then, don't worry so much about it and do it the long way. But they don't need to see all this work on the AP. I don't need to see all this work on the AP. I'd be happier knowing that you understood that when you take an antiderivative, you need to maintain your center. So if you're centered at x equals 4, then this guy needs to be centered at x equals 4 as well. Okay, I have D. D, and then we'll probably stop here. Can the exact value of f of 3 be determined from the information given? Justify your answer. Well, this is centered at 4. So no, I cannot find the exact value of f of 3 because if I wanted f of 3, I would need an infinite polynomial that matches a function, and I need to know its interval of convergence and all of that. So can the exact value of f of 3 be determined? No, because p is only an approximation. It is not the actual value of the function, okay? Okay, here's what I'd like to try next. I'd like you to try this one on your own. I know it seems crazy, just do what you can. I'd like you to try this one on your own and then come back and I'll go over it with you. All right, now I know this one looks scary and I'm sure a lot of you are thinking, I'm just going to watch her go through it, and that's okay. But basically what I want you to get used to is you have to just use what you're given. So the Taylor series about x equals 0, so a certain function converges to f for all intervals in the x and the interval of convergence and add to the... There's a lot going on here. So let's just take a little piece. Here's a big chunk of a formula that we don't really know what to do with yet. But it tells me that if I want the nth derivative at 0, I just plug n into this function whenever n is greater than or equal to 2. In layman's terms, this just means if you want the derivative, plug in numbers for n here, okay? Well, I need derivatives because those become numerators, so that's what I might want to use this for. They also tell me that the graph of f has a horizontal tangent line at x equals 0, and that f of 0 is 6. Okay, that's okay too. A, determine if f has a relative max, relative min, or neither. Well, what do we remember about that? Something has a maximum when it has a 0 for the derivative and it's concave down. So I have a maximum when the derivative equals 0 and it's concave down, or if the derivative doesn't exist, but they tell me that the derivatives do exist. So I need to show that the derivative equals 0 and that it's concave down, or derivative equals 0 and concave up. Well, wait. F is a horizontal tangent line. If I have a horizontal tangent line, then f prime does equal 0. And now I need concavity. Concavity is, oh yeah, that's the second derivative, and this will tell me the value of the derivative for when n is greater than or equal to 2. So if I want the second derivative, I plug 2 in for all of these n's, and I get that, negative 6/25. Therefore, since f prime equals 0 and f double prime is less than 0, f has a relative max by the second derivative test. All right, next piece here. Write the third degree Taylor. So if I need the third degree Taylor, I need the 0th derivative over 0 factorial. Well, that would just be 6. I need the first derivative. Well, we just said that's 0. I need the second derivative over 2 factorial. I just got that from here. And then I need a third derivative over 3 factorial. And that's what's underneath this happy little heart here. Here's the 0th derivative over 0 factorial x to the 0. The first derivative was 0. That's why there's no x term. The second derivative was negative 6/25 over 2 factorial x squared. And the third derivative was this guy. Well, 4 factorial, 5 cubed, 2 squared over 3 factorial, fine. There's your third degree polynomial. Now you can leave it like this, or you can simplify it, and if you simplify it, it turns into that. Honest to God, you can leave it like this if you want. All right, and then last but not least, write the general form. What? I don't see a pattern here. That's okay, we actually don't need a pattern for the general form. The general form is just the nth derivative over n factorial x to the n. Here's the nth derivative. They gave it to us. So for this one, I took the nth derivative by just transposing that big function and putting it on top. Nth derivative over n factorial x to the n. Then I simplified by doing something really cool here. If you want to talk about how factorials cancel, if you have 7 factorial over 6 factorial, doesn't that just equal 7? Because this is one bigger than that, and you'd have 7 times 6 times 5 times 4, and 6 times 5 times 4. So those would cancel, and you just have 7. Same thing happens here. This is like 7 factorial, and this is like 6 factorial, and these cancel and just leave the 7. So factorials are really fun to cancel because they cancel in kind of a unique way. So I canceled those and just wrote it like this, and there you go. That's your general term. Okay? So there's a bunch of Taylor series. I am definitely over the mark that I wanted to stop at. So 2 pirate jokes for you. Um, why can't pirates play cards? Because they're always standing on the deck. And why are pirates so mean? I don't know. They just are. Okay, I know those were bad, but maybe you enjoyed them after 23 minutes of some pretty intense calculus. I hope you have a good day, good morning, good night, good whatever it happens to be, and I will see you guys later.